recording the presentation?
I'm not sure. Does it sound like that?
Because your presentation will be. Oh, wait.
All right, time to get started. How many of you have gone back home and did this derivation that I showed in the last class and you understand this? How many of you still don't understand it? What does it mean? Like, where are you right now? If I ask you to pick a side, like yes or no, you understand versus you don't, which one you will pick? Yes?
Yeah.
How many for yes? Okay. Okay, I could see still some hands not raising. So we'll quickly go over what we talked about in the last class. How about this? All right. So remember, we had a likelihood function that we said we want to optimize, right? And one big benefit of this is now you have a formal optimization problem where even if your data is not linearly separable, you can still learn something that you couldn't do with perceptron. Because now you are trying to optimize a function. It doesn't have to be exactly linearly separable. But still you are learning something, a linear separator, with respect to a cost function that you are trying to optimize. So what is our likelihood of W? How did we define the likelihood of seeing the data given W, right? And we said like we are going to talk about the conditional likelihood, right? Because this is the discriminative classifier, not the generative classifier. So we talked about, we have a training data set, right? We have our training data set like this. Now this training data set, and we are trying to learn a W that can explain this data, the training data set. How? What this data will do is it's trying to compute a dot product with individual X to predict the Y hat. And the W that, see, this X can always change, Y can change, but W doesn't, right? That's the knowledge. So now, if I multiply W with this, I want to get this. If I multiply W with this, I get this, but not always. My W may not be able to perfectly classify, or it may not have the highest accuracy, like the 100%. But the goal is to learn a W that predicts the correct label, right? And what did we assume about this prediction? The prediction was the function of X is essentially 1 divided by 1 plus e to the power minus W naught plus sum over I Wixi, right? Is that clear? And we said this is essentially a Z, like we can call it Z, right? So this is just a logit function. It's a sigmoid function, right? It's a logistic function. There are many names for this. And this is just the dot product. Okay? Now, we said because now we have a probabilistic interpretation, we can compute the likelihood of the whole data. And we said, like, computing the likelihood, like estimating the likelihood of the whole data set is a very sparse problem, right? Because every data set is kind of unique. So rather than computing the joint probability of the whole data set, we kind of made an assumption. What was that assumption?
IID.
Yes. I want to hear from the back. What was the assumption?
They're independent.
Who are independent?
The attributes.
Attributes. Are we assuming attributes are independent here? Is this naive Bayes?
No, it's not exactly naive Bayes.
Then what is independent? Yes.
Like each individual point is independent from each other, and they all have the same probability of appearing in the data.
Exactly. Two different things. One is the feature space, and the other one is the data space. So here IID essentially means these data points are independent of each other. Whether you have seen X1 has nothing to do whether you are going to see X2 in the data set or not, in the training data set. And each of them has an equal probability of being in the data set, which is different from X1 is actually a collection of features X11, X12, X13, one, let's say D. This is the feature space. And in naive Bayes, we make an assumption that these features are independent, not the points themselves. Yes, question.
I guess I'm just very confused about the difference between when you say data and the features. Isn't the features the data?
Features are coming from one data. So you can think of this, the simplest one is the row and the columns that you see. The columns are essentially the features, and the rows are the data points, right? And each data point is represented by some features. In naive Bayes, we made an assumption on the columns. In the IID, the assumption is on the rows. Is that clear? Okay, so because we made this assumption, we can now write it like a multiplication, right? And we said we are not going to care about the joint probability of X and Y, rather the conditional probability, because that's what is the definition of a what kind of classifier? Discriminative classifier, exactly. That is the definition, excuse me, of this. This is the definition of discriminative classifier. Okay? And this is going to go over all the possible J in the data set. So far clear? Why can't we write this? Is that clear? Because we are assuming these data points are independent. So I don't need to write one single probability that will give me all possible XY pairs. X1, Y1, X2, Y2. The whole data set has some joint probability. That is very sparse problem. That is hard to estimate. We cannot. So we are making that IID assumption with the definition of discriminative classifier to have this conditional probability multiplication. It's very important to understand. If I give you in exam, I saw some people were like looking down and then they looked up in exam. I'm going to give you a function, maybe not exactly like this, and I'm going to ask, tell me what are the assumptions I made here. Right? You don't need to memorize anything. You need to understand what the implicit assumptions mean. Okay? Here, I made conditional, I made the assumption that the discriminative classifier is the right classifier. I also made an assumption that data follows IID, what it means, right? So those are the assumptions we are making here. Okay, now take a log. Why? Because that simplifies many different things, like multiplying many probabilities into smaller numbers, underflow error, zero probability multiplication, all those problems are gone, and you are still optimizing the same function. So you have sum over j log of this, right? Clear so far? Good. Then what? Then we said we are going to replace this term with the actual probability that we are estimating. And what is the definition we are using in logistic regression? This is the definition, right? The probability is estimated using this formula. So this is essentially probability of yj given yj equals to 1 given xj w, right? This is the definition we have, and then there is another part of this, right? Yj can take two different values, so it could be 0. Xj given w, and here if we just say that this is e to the power minus z, then this is 1 minus 1 divided by e to the power minus g, which is e to the power minus z divided by 1 plus e to the power minus z. Right? Now to simplify the computation, still we can multiply on the both terms, like on the upper term and the lower term by this. So the negative part is gone. Right? They're essentially the same thing. Yes. Xj is one data point. Yes, xj is one of these data points. You are trying to classify xj into some y. And this xi is a feature of that x. So I is the index for attributes. J is the index for rows. And I is the index for columns, yes. I mean, it's a big X. Yeah. Is that clear?
So you said I is columns, J is rows?
Yes. Yes. Right? Let me just make it a big X. That will help. Okay. So now we have two possibilities. And xj in the training data set could either be 1 or 0. So I need two formulas. I need a if and else. And that is a problem with this kind of mathematical compact notation, right? We need a single formula. And there is this trick that we used. And that trick, I still don't know the name. I forgot to check it. But the idea is to replace this with two possibilities. So one possibility is when yj is positive, what you can do is to write like this, to the power yj, the positive case, because that's what the probability is. If it is negative, then you just multiply with 1 divided by 1 plus e to the power z, 1 minus yj. Yeah. Right? Is this clear? Questions? Good. So now let's divide the log. So if I apply the log, what happens is yj comes in the front, log e to the power e to the power z, 1 divided by 1 plus e to the power z, plus 1 minus yj log 1 divided by 1 plus e to the power z. Clear? Now we can simplify this term further by saying log e to the power z minus log 1 plus e to the power z. Which means, what is log e to the power z? Log e to the power z. Z. Okay, so this becomes multiplied with yj, and yj also multiplies with this term. Right? This part. For this part, we can break it down. The first part becomes log 1 minus log 1 plus e to the power z, right? Minus yj log 1 plus yj log 1 plus e to the power z, right? So log 1 is 0. So this is 0. This is 0. Right? So this part is equal to this. So we can get rid of this. And this is what we get. But these two are equal. So they cancel out. So now you just bring this term, log 1 plus e to the power z. Over all the j, over the whole data set, right? For each row. Okay. And this is what you see here, right? The log likelihood function is essentially this, where they just replace the z with the actual formula. And what is that? The dot product. Z is essentially the dot product. Not plus wixi minus log 1 plus e to the power w naught plus wixi. Yeah. Okay. Okay, so now there is some good and bad news. What is the good news? We can compute our likelihood function. That's the good news. What else?
Handle both cases in one.
Handle both cases in one. Very good. How about optimizing for it? This is the function. We haven't yet optimized for it. We want to optimize this function. Actually, we want to do what? This is the likelihood. Do we want to maximize or minimize? Maximize, right? This is not a cost that we want to minimize. This is the likelihood that we want to maximize. There is an equivalent cost function. If we invert the function, that's true. But as it is, the likelihood function we want to maximize. What kind of functions are easiest to maximize? Ones that are differentiable, okay. Is that the easiest case? I mean, it has to be differentiable in order to compute some gradients, but is that the easiest? Okay, tell me this. Which function is easier to optimize?
The right one.
Why?
Well, it's easier to optimize assuming you know that there's only one peak. But if you do know there's one peak.
I mean, you know everything that you see here.
Good. Then knowing that, the right one's easier because you can just follow while you're increasing, and then once you're decreasing, you found it and you're done.
Okay? So, this kind of functions where there is, you see this is kind of a maximum point, right? I mean, if you go either way from here, you are decreasing the value. But then again, there is another like peak like this, and there are more peaks. So these are called local optima. And this is called the global optima, which is the overall optima, right? What is this? What? The only optima. So it is both global and local, right? So the only optima. So this kind of functions has a particular name. What is it? Yes. Is that convex? Sure. What kind of function is this? Both are differentiable. They are continuous, right? Parabolic. Okay. I mean, its shape is parabolic. That's true. But if I do something like this, still you could say that's a parabola as well, right? I mean, like this. But in terms of optimization, it has a name. What is that? Quadratic. I mean, this is also quadratic, right? The square. What? No, it's not, because then you'll have multiple ups and downs. So it's called concave function. Okay? And for every concave function, there is an equivalent convex function if you just flip it. So minus of f. Yes?
What's the definition of a concave function? Just that it has only one maximum?
If you take the definition of concave function is, that's a good question. If you take any 2 points on the function and connect them with a straight line, every point of that function within that range should be above that. And for a convex function, it has to be something like this. If you take 2 points here, within that range, every point should be under that line. And they should be differentiable. So, if I take a gradient that tries to find the direction of the maxima, and that will be the global maxima, because if it is a concave function, and fortunately this is a concave function. Proving a function as concave is not always easy. You can test concaveness of a function. Theoretically proving something is not trivial. But if you test the properties, this turns out to be a concave function. That means there is one single global optima. And that you can maximize by computing the gradient, because gradient gives you the direction in which the function maximizes. And that's why this kind of function, where you are trying to maximize a concave function, is called gradient ascent. And in the counterpart, when you have a cost function, that is a convex function that you are trying to minimize, the similar kind of methods apply, where you compute the gradient, but instead of going in that direction, you go in the opposite direction, because gradient is giving you the direction to maximize, you go the other direction to a minus, that is called gradient descent. Clear? So here, now we can do gradient ascent to maximize this function. Or if we just switch this function, take a minus of this, we can do gradient, instead of gradient ascent, we can do gradient descent, because that function will be convex. Okay? All right. So these are all good news. And the bad news is you still have to sum over all the whole data. There is no closed form solution that gives you the final answer. You have to go over the training data set and kind of look for, compute the likelihood, and also you need to maximize the likelihood. There is no, because this is not closed form, the derivative of this is not going to be closed form. That's the bad news. But we can always do iterative updates, right? Like gradient ascent and descent. That's what we are going to do. So now the point is, we are going to update the weights, right? We have some weights, let's say, and we have a vector of weights. So vector of weights, W0, W1 till WD, let's say. So for a particular weight, we have to update, let's say WK has to be updated for t plus 1 as WK, the previous one, plus. We have a plus here. Why? It is gradient ascent. That's why. And then you have to compute the gradient of W with respect to K of the likelihood function, and you make a step towards that with some learning rate eta. That is the learning rate, because you may not want to take the whole step towards that direction. You may want to be a little conservative, or you may want to be a little more aggressive. We'll see what it means to have different kind of learning rates. But the whole idea is you just use a scaling factor on the direction of the gradient, because we are optimizing a concave function. So essentially, you need to take partial derivatives because this is a gradient in a vector. So for each component of this vector, you need to do a partial derivative of the likelihood function. And that's what we are going to do. So take a partial derivative of this function. This function. Essentially, that means wk with respect to the whole function. To the whole function, which is sum over j yj w naught I wixi minus log 1 plus e to the power w naught wixi sum over this and a third bracket close. Now all we have to do is to compute this derivative, right? So let me first add these two like multiply y j into both these terms plus yj. Just multiply. So if I take a derivative of this term, first term, what happens? With respect to wk?
0. No.
Y
it's
is
the
0?
same. It's the same.
Is the same. Why?
W naught plus y of j.
What? Yes.
It should be 0 because there's no WK.
It should be 0, right? Because there is this variable is absent here. Everything is constant,
Constant.
with respect to this wk. So that is 0. What about this?
They're all zero except for the one containing WK.
Yes,
WK.
they are all 0 because the only term that has wkxk we need to consider. Others become 0 because they are constants. So what we have is essentially yj wk. Actually, with respect to wk, you only have xk, right?
Yep.
Xk. And summing over I, so this is xk I. So actually k and I becomes the same, right? So this is the k and this is the j. Because you are doing it for each possible. So if you think about this term, this is actually the ith column of jth row. Because you're summing over all the j. And j is each example. So that j is already implicit everywhere. The only thing is we are replacing I with a k because only for this k, this term is non-zero. J is a summation over all the examples in the data set. Okay, so this is the right term. Okay, and what do we do here? We apply chain rule, right? We apply chain rule to this part. So let's do a minus. And then we have a log of this, which is essentially 1 divided by 1 plus e to the power this j and what we do is we apply chain rule e to the power xi j and then we apply again here which is xk. Okay. Right? But this part is already our definition of the probability in terms of the logics. So what we do is essentially, still we have this sum over j, yj xj of k minus xj of k, probability of yj given
xj.
xj and w. You can keep k or not, it doesn't matter, it's just a notational thing. But the whole point is, you can now compute the gradient of this function with respect to this simplified function, and we can further simplify it by saying xj times this. Okay? And this is just for one component of W. You can do this for each component of W and update it in a vector fashion. And how is this different from our traditional perceptron? In perceptron, we will add x or subtract x, right? That's what we did. In perceptron, what we did is Wt plus x for positive error,
Yep.
and Wt minus x for negative error. But here, what we are going to do is still we have a vector component, that we still had there. So we will add the same x or do a subtraction, but with some degree. And that's what we kind of train this formula as how much error I am making, and then I will try to adjust my weights with respect to the degree of my error, which basically means here, no matter, every time you make a mistake, you make the same update. But here, it's not like that. Every time you make a mistake, you do the same update. For example, if yj could be 1 or 0, right? So if yj equals to 1 and you predict 1, so your model that you have trained, you are learning, the probability, if you compute with respect to that w at a particular time t, if that predicts also 1, that means 1 minus 1 equals to 0. That means this is 0. That means you don't do anything. That means you made a correct prediction, so you should not do anything. Right? This is probability of yj equals to 1. But again, if yj equals to 0 and you are predicting probability of yj equals to 1 equals to 0, then again you are correct, right? Well, 0 minus 0, 0, you don't do anything. Same as perceptron. If there is no error, don't do anything. But in difference comes when there is an error. In perceptron, it's just a binary decision. You made an error, add x. It's very, very, very kind of drastic action. Right? Your head is burning, cut off your head. But here, it's more like, okay, let's first try some medication. Right? So if you have a 1 here and you are predicting that the probability of this one being 1 is 95%, that means you are already pretty good. So the amount of update you should have made in perceptron now becomes only times 0.05. So you make a small change. But if you actually, your classifier is terrible right now and it is predicting 0 for this example, that means it is making a huge mistake for this particular example. It has to be taken seriously. It's not like a boundary error. It's very like kind of making a complete opposite prediction. So now you need to take drastic action. Now it's time to chop off, right? So that means if it is, the difference is 1 minus 0, that is the maximum difference. Then you add the full amount of x. That is what you do here. Or if it is 0, but you are predicting this to be 1, again, a big mistake, drastic action. But now it's negative. So you are subtracting this example like this, or negative error. But if it is in between something, you are only adjusting x, I mean the weights with respect to a weighted x, not the full x. And this kind of flexibility now gives you the power to optimize for a linear classifier. Okay, why am I still talking about a linear classifier? Is logistic regression a linear classifier?
Yes.
Why?
The decision line is still linear.
Still the dot product, right? It's still a plane, right? So now something, if you have something in between, so there is some tolerance to the model. So even if your data is not completely linearly separable, this function can still work to optimize. It will try to minimize the error. In perceptron, there is nothing. If it is not converging, you cannot do anything. Is that clear? How many of you feel like you have a better understanding of this derivation today than you had last day? I'm happy. Thanks. Okay, because the last day the heads were like very depressed. I didn't feel good about it. And we have covered all of this. This is the output. Ready? Yeah. Yes.
So are we always going to go through like from J to like the whole data set for each thing that we're calculating on?
Unfortunately, yes, because you want to learn from the whole training data that you can.
So like on each row, it's going to do the whole thing for each time?
Yeah.
Okay.
Yeah. Okay, so let's talk back about, so think about this, right? So this is the update you can make, but there is more things that people sometimes do is by adding another eta here. So you can further scale the number of like changes, I mean the amount of change, the degree of change you want to make. That is called the step size, the learning rate. You have already seen this in your perceptron assignment, and you had question, and I just set it to 1. But it doesn't have to be 1. It could be smaller. It could be bigger. And what is the right one?
0.
What is the right eta?
The one that maximizes the likelihood function.
Oh.
Between 0.01
In
to
the back set, what is the right eta? Any idea?
Changes for every data set.
Changes for data set, okay?
You're looking for an actual number.
I don't know. You tell me. There is no right eta. There is no right eta. Right? That is a hyperparameter that you want to optimize. It depends on your data set. It depends on your application. It depends on trial and error. Yes?
What is the impact of eta on the classifier?
Exactly. That's where I'm coming from. This is the impact. See, you are trying to optimize for this function, right? Now, here, if the step size is big, that means you will jump from there to here, and once you come here, you will keep juggling. You can never reach this point if you don't adjust the amount of eta that you are actually making a progress. Yes?
Do you adjust it after you go through your whole training set, or do you adjust during?
Well, first of all, you don't know this function. That's the real problem, right, in machine learning. So you don't even know where you are. The only thing you can do is to try to tweak eta and see whether your likelihood is increasing or not on a training data set. That's all you can do. So yes, you have to go over the training data set. to really test this because you don't know this function. If we knew this function, there is no point of machine learning, right? We're trying to learn this function, no, not exactly this function. We're trying to learn some other function that gives us this kind of likelihood function that we are trying to optimize. So because we don't know the original function, we don't even know what the likelihood function is, the real one. These are all in our head. If you have a very small one, then you will converge, but you will take forever. Given a very large, complex network where you have to do a lot of updates, and neural networks are classic examples of this in deep learning. If you are not taking enough steps, think about walking to India from US. Not a very good idea. So that's the problem. So you kind of want to tweak the EDA that kind of takes you quickly to the optimal point, but also you don't miss the optimal point just because you are jumping too much. Okay? Yes, you can. So there are ways, like initially when you start with a model, you can have a larger eta because you are exploring, but once you are converging, you want to make eta smaller over iterations. So that at the end, initially you make longer jumps, but at the end you make shorter jumps to actually ensure you are converging. Yes. And then you can always do, for example, for this kind of functions, whatever you do is not going to be enough because you start from here, you are stuck here. Then you need to do random initialization. Maybe you start from here again and see. Start from here and again see. Start from here and again see. And then take the global one, whatever you have seen, hoping you have explored enough. Question?
So you could, after each epoch, just if the error or the accuracy is lower, then you don't actually take that epoch, you have the learning rate, and then try again? Something like that?
Yes, and that is a question that has to be jointly answered by computer science and business. Because whatever that error, is that okay? Right? Because how do you define the error is, what is your definition? This is a minimum error or this is a tolerable error. That depends on your business application. Okay? And the final part is, you see, this function is almost the same. What is the difference here? The updates that we see here, the W star, we are trying to maximize essentially this function with a little change. And what is that? Essentially the same. If I take the log out, it's the original multiplication term, optimization of this. But what is new?
Probability of W.
Probability of W, that is not here. And what is probability of W?
Probability of here.
What? What is its role? Because we are multiplying this with this. Remember Bayes. What do you get? What is this versus this?
Two independent.
Okay, what is this? What did we call it, the function?
Likelihood.
What? Likelihood, right? This is likelihood. What is this?
Probability of likelihood.
What do you call it?
Prior.
It's a prior. Yes, it's a prior. And if you multiply prior with likelihood, what do you get? Posterior. Yes. So this is now basically saying you can do similar kind of analysis, and this is coming in the exam, right? No? because now you can multiply this likelihood with a prior. So you can put a strong belief that W should be something like this. I know. I have, from my 10 years of experience, I think W should be something that follows this distribution. And I can tell you, like, okay, let's say PW follows a Gaussian distribution. What happens in that case? Right? And then it is like imposing some prior and regulating the W that you want to learn. Because here, W is entirely dependent on the data. But as human, as an expert, as a domain knowledge, you could say, that's fine, but W should also look something like this, similar to this. So then it will make a trade-off. It will adjust based on your prior belief what W should look like and what W you learn from the data. And you combine them to see what the actual data W should look like, optimal. That is the posterior map estimation, maximum a posterior. You are trying to maximize the posterior distribution rather than the likelihood only. And imposing this kind of prior is called regularization, which is one of the most important tasks in machine learning. Imposing this prior is called regularization. This is more like controlling. This is more like, yes, your data tells this should be the W, but from my experience, I know this should be the W. So let's make a trade-off. I will regularize what possible Ws can actually be accepted. Yes?
So is the prior, if you're doing an online algorithm, is the prior like the last round what the W was adjusted to?
You know your prior before you have done any iteration. That is what prior is defined. That is what your 10 years of experience should tell you before you see the data. Think about this. Some company, you have worked at Amazon for 10 years. Now Walmart is saying, like, we want to improve our online customer experience and we want to beat Amazon. And you have a product database where you are trying to maximize the likelihood of the clicks. From your experience, you should be able to tell what kind of weights should maximize click. But then Walmart's data might tell you otherwise, and then you make a trade-off.
Is there ever a problem with like trusting that old prior?
There is always a problem. If your prior is wrong, if you're making a wrong assumption, that's a big problem. But if you're right, that helps. Because your data, as you know, this function, if that gets complicated, your data can already be misguided with the training data. But if you make the right prior impose, it drastically can improve the performance, or it can completely doom you. Right? Question? Yes.
So if your prior is bad, do you just get rid of it? Like,
if your prior is bad, if you don't have a prior, just don't use it because you don't know. Just trust on the data. Yes.
So I'm trying to visually understand in the perceptron when it draws the decision boundary, it's like a linear plane. Does it ever have any curvature where it curves around like the data?
No.
It's always just flat.
No. Perceptron, the model that we learn, unless you use some kernel trick that we are going to learn after the midterm. Or do you want it to be part of the midterm as well? No, you don't. But to curve it, you need to do kernel trick, and that's what is coming after the midterm.
So
Yes.
would that just be like, you would have a curved graph, but then if you throw it in another dimension, it could be seen as straight?
Yes.
But from the proof.
You could do some transformation, which is called a kernel function, that can transform your data from this space where your data is kind of very convoluted, mixed, and like hard to separate. It could do some intelligent trick to transform it to a higher dimension where it is actually linear. That's the trick. And then we know how to solve linear problems. So just combine the two. All right? Good. God, I still have 15 minutes. Okay. So let's start the next lecture.
I mean, you just did it now. I mean,
Yeah, I could. I could, because this is what I have taught so far defines your midterm syllabus. The first midterm. What I'm going to talk now, if I tell you right now it's not going to be in midterm 1, you will not listen to me, right? Believe? But yeah, just listen to me for fun. I don't know. Is this course fun? I don't know. I'm trying to make it fun.
It's fun.
It's fun.
But
I mean,
yeah.
the applied part is fun,
The theory part is not.
theory part is a little fun.
Well, I have heard the opposite. Like some people say, the theory is so fun. When it comes to coding, oh, that's a nightmare for me. I don't know what's the right answer of this, because it's again the optimization between prior and the likelihood. Right? Wanted to say something, Hugh?
I love the theory.
Okay, yeah. You see? I have seen all kind of it depends on the background. But yeah, I know why this happened, and this is natural, because here we have software engineering undergrads who are entirely focused mainly on practical issues. Theoretical computer science student who has good understanding of probability and all those theoretical. Some people come from math background. For them, theory is great. And then don't take it personally. And then there are students, graduate students, who doesn't have computer science background or even sufficient probability background, but they are interested in applying machine learning to their particular research problem. But they kind of join this and find out, oh, I'm not yet ready. That happens as well. Just because AI is now fancy and everybody wants to apply this and everybody wants to go enroll in machine learning, and sometimes people think okay, if I download a scikit-learn library, I write 3-4 lines of Stack Overflow code, I am doing machine learning. Trust me, you are not. This is machine learning. Okay. All right. So let's go back to the stat class again. So this is now, again, we'll go back to regression, but this time is the linear regression. So no longer classification. We now move back to the regression problem. This is completely new, and we haven't covered this yet. And why? Because we have been focusing on classification so far. And classification is one of the crucial tasks in any pattern recognition. Like you have some predefined classes, and you want to assign labels. You want to recognize patterns and label them. But at the same time, there are problems where you want to predict continuous variables as well. What is one example? Stock market, right? How many of you invest in stock? Wow. I started investing when I started making money as a professor, because when I was a graduate student, I didn't make money, so I couldn't invest. But then around 2020, I started investing, and it was booming market. And then COVID happened, right? And I lost around $10,000. So I left stock market forever. Well, let's not call it forever, but yeah, I don't go back to I use Fidelity, so I don't go back to that website now. Maybe sometime when the market is back.
Made more since then.
If I had a good stock prediction model, I would have quit. Well, it's not that I entirely made losses. I also made a lot of money. That's why I invested more, and then the time comes. Nobody can predict that right time, right?
Remorse.
Yeah.
So have you tried to write a machine learning algorithm for the stock?
For stock, I have not, but then I have worked for a company during my PhD as an intern, where the company is called Jump Trading, and their job is to do automated trading based on algorithms. I worked on a part where they were working on Twitter and Bloomberg News to identify sentiments about a company. And then they were using that, whatever sentiment I derive based on my NLP model, they are going to predict they're going to train another regression model that will predict the market. And don't ask me how that went, because I don't know. And probably it was bad.
So that problem has not been solved yet.
It can never be solved, right? Because if
Or are there
You only
firms
need a
that have
good
secret
accuracy.
algorithms that
there are, I mean, if you go to New York and what is that street called? Wall Street?
Yeah.
Everybody is into that, and also in Chicago, yes.
But then, like, when you do have that model that solved it, it'll be going against other models that have also solved it, and then they're competing, so
Yeah.
they can't solve it.
Yeah, you cannot solve it.
Compete each other.
And then it's hard to predict, right? The point is, stock market has so many variables, and you see, with like very few variables, what is your life? To really capture a real world, do you really think like we are at that stage that we can capture the real world? This is entirely virtual world, still machine learning. The AI fancy that you hear, everything is still in a virtual world. It doesn't really connect to the real world yet. And that's why we still have our job. We are doing some research. Otherwise, we are out of our job. Having said that, tomorrow at 10 a.m. in the morning, there is an excellent talk happening on natural language processing research. Here, a very famous professor from Pennsylvania State University is going to come. His name is Dr. Dr. Shamir Wilson, okay? Shamir Wilson, and he has written excellent blogs about students. Like how should you manage your expectation? How, if you're trying to do research, how you should communicate with your advisor. And of course, he does excellent research as well. So if you want to meet him, please be there at 10 a.m., third floor in the seminar room, computer science, okay? If you can make the time, you will like it. And why am I telling this? Because I am hosting him, so if I can bring more people, that credit goes to me, okay? If you are attending, tell me and I will give you 1 point bonus for your course, okay?
Oh, thank you.
Does that help?
Yes.
Okay, maybe 5 points.
Definitely going. You sold me on one.
They have some proprietary data that
Modeling.
that company purchased. So it's basically news about from financial experts, like what is going to happen to this company or how this like merging or like acquiring of a company went, something like that.
So people write reports. And
Yeah. And then we are trying to, for example, if Microsoft acquired LinkedIn, it's a positive sentiment for Microsoft, something like that. It's also positive for LinkedIn in some way. So it depends on how you create the labels. Yeah.
I read an article, somebody trying to do that with earning calls, and earning calls are so full of fluff that it just turned out like everyone was positive.
Yes, and that's why this is a so hard problem. People thought like, oh, just monitoring Twitter, writing some algorithm will help me predict the market. Turns out, who is that person like in New York? It's like you follow, everybody follows him in the market?
Michael Burry.
Warren Buffett. It looks like following Warren Buffett is a better idea than using those algorithms. So it's a hard problem. Humans are still better at something, right? Okay, so we still have 10 minutes. So we are going, so this is exactly what we talked about so far. Stock market. What else do you think we can do with regression problems?
Disease. Viruses.
What?
Tracking the spreading of like diseases or viruses.
Tracking pandemic, right? Like tracking the number of deaths or hospitalizations due to COVID, for example. You could try to predict how much support you want to provide to the local hospitals and all that. So that's very important. What else?
The rockets or satellites, the orbit or the the path of the rocket while it goes up according to already traveled path.
So if you have a particular goal in the space, and you are trying to send some what is it called, like air space
Carrier.
what
Carrier.
space carrier, okay, space shuttles, let's say you want to send in a particular direction that optimizes for a particular function. You can also do that, frame that as a regression problem. Yeah. You could predict weather, what is going to happen tomorrow, or maybe in the next hour. You could try to estimate contamination based on you sample data from some particular places and look at the level of contamination there. From that, you could kind of extrapolate or interpolate your data to actually figure out which regions are more contaminated than the others. So you could do cool geoscience stuff with this, right? So, and then so far we have been talking about, and regression problem itself again, you have a X and Y, right? That's what we have been talking about. X is your input, Y is your label, Y is your output. But here, Y is not a label, Y is what?
Another
What?
another point.
It's a continuous variable, right? It's a dependent variable. It's the target variable, but it is continuous. That's the only difference. Okay? So this X and Y kind of training data, and what do we call it, this kind of learning? Supervised learning, right? Because Y is supervising. Because you think about all the whole learning. Everywhere, you look at the label and whether you are making a mistake or not, and based on that, you learn something. So Y is kind of supervising W with respect to X. You see what I mean? So there is some W you want to learn. And I think you have so far, like at this stage, you should understand that machine learning is all about learning the W. X is given, Y is given in a training data set. You don't know the W. From X and Y in the training data set, you figure out the W, and then in the testing data set, given X, you apply the W to figure out Y. That is machine learning, right? I mean, at least the supervised learning setup. So same thing here, just that Y is continuous. Okay? So here is the thing. So in classification, we had some kind of cost function, and vice versa likelihood function, that cost function that we wanted to minimize or likelihood function we wanted to maximize. So essentially, we were trying to minimize the classification error, right? If I'm predicting a label of dog instead of cat, that is an error, and I don't want to do that. I want to minimize that classification error mistake. That is the goal in classification. What should be the goal in a regression? Because in classification, there are a finite set of levels, labels, and you can kind of try to match with the label. But in regression, it's continuous. It's infinite possibility of values. Then what should be our ideal goal in regression?
Minimize the distance between your prediction and the actual values.
Right. Get as close as possible to the real value, right? If the stock price is 95, try to predict 94.5, I mean something that is close to 95, so that you can make a good decision. It's very hard that you will find the exact number 95.0003789, something like it, right? So the goal is not to find the exact label, but try to minimize the error between the actual value and the predicted value. And one popular function for this is called mean squared error. How many of you have heard about this? Mean squared error. How many of you have never heard this term? Okay, so mean squared error is basically the expected value of your prediction minus the original value, the real value squared. The difference of the square of the difference of the real value and the original value. Did I say real value and original value? I should not.
Expected.
The expected value of the expectation of the square difference between the predicted value and the real value. Okay? It's a simple goal. Why are we interested in a difference? I mean, square of a difference. Why does it matter? Yes?
Negative error.
Negative error, okay? Negative error becomes positive. Or anything else that can help? Yes. Big errors matter more? Yes. What else?
Easy.
We don't want positive and negative cancel out each other. Yes? Yes?
We precisely know how far away from the actual path we are from, like.
But
That is good.
that can be calculated without a square, right? Point is y square.
But if we have something.
Can eliminate minor errors because the square is much more minor than the error you made. Can neglect them.
All these are true, but there is one more motivation. Think about optimization. What kind of function is this?
A minus B.
What?
Parabolic?
Parabolic, okay? Concave?
Convex.
Convex. Okay. So this is a convex function, and you can minimize for this error. It's very easy to optimize, so that's another reason. Okay? All right, so in the next class, we will go with one of the linear regression techniques where, again, you have a linear classifier. You see, that's a dot product. But that dot product is going to give you a continuous value. And you are going to, that f of x is essentially a dot product like this. But you are going to match the output of the dot product with the real y value, which is continuous. And you are trying to minimize the sum of that squared error instead of what we try to do in the classification problems, right? Here, we are trying to minimize the squared error. That's the only difference. And we will continue next week. All right? Thank you very much.
Library can look